So in its entirety, beams have been completed along with one-way slabs. So we are still going to continue with flexural elements. Okay. So flexural elements in the sense elements which take bending. One of them is beams. The other type of structural element that takes bending are slabs. So one-way slabs we have already seen how to design them because we were able to say that a one-way slab is nothing but it can be designed as a beam of 1 meter width or unit width spanning in the direction of the shorter direction or in the direction of whichever two edges the supports are. Okay, so based on such a principle we were able to decide that uh, one-way slabs behave similar to beams, and same principles you had used for designing one-way slabs as well, except some specifications with regard to the design, such as the diameter of the bar that you can give, thicknesses that you can, the Lbd ratio which you can modify. Okay, except for some such specifications with regard to slabs, everything else was almost the same design procedure as you did for beams. Now the one remaining element, remaining two elements which undergo bending kind of a behavior are two-way slabs and staircases. Okay, among this staircases, I will not cover much. Okay, in fact, that will form a part of your assignment. I don't think I have given any assignments till now. So that's what I'll do. I'll be probably giving an assignment on staircases. Okay, which you will do as a self-study, and you will actually do some design problems as well. So we'll start off with two-way slabs. So going back to what we studied when we were doing one-way slabs, we saw this major difference between one-way and two-way slabs, meaning that any slab which is supported on either two sides, or if it's supported on four sides and your long by short ratio is greater than 2, then it's a one-way slab. Okay, and any section parallel to the shorter direction, or any section which is parallel to the direction along which the bending takes place, will behave in the same way. Okay, so if you look at this picture which is shown over here, two things that you can notice is over here are, if you take any section, if you take a section over here, it is curved. Take a section over here, it will be curved. Take a section here, it will also be curved. If you come in the other direction, which is if you come from this end to this end, you take a section here, this is a straight line. You come here, this will be a straight line. Only thing, it will be a little bit down, but all sections parallel to this will be straight lines. All sections parallel to this direction will be all curves, which basically tells you that bending takes place along only one direction. Okay, so this is what a one-way slab is, and on the contrary, a two-way slab is something which is supported on all four sides, and the long by short ratio is lesser than 2. Okay, that is the technical definition of a two-way slab. And on contrast with the one-way slab, if you look at the deflection along two perpendicular directions, you take any section parallel to LA, it will be curved. Take any section parallel to LB, that will also be curved. That will also have a curved deflection, more or less. So that is behaviorally the difference between one-way and two-way slabs. This is something that has already been covered to you when initially discussing about one-way slabs and what the difference between a one-way slab and a two-way slab is. Okay, so now when you come to one-way slab, or any slab which is actually supported on all four sides, it's not just a one-way slab, even not just a two-way slab, even for one-way slabs. If you have a slab which is supported on two-way sides, all four sides like this, okay, this is how you calculate how much load comes to each of the four beams. Okay, so let me say that I have a slab. It's supported on all four sides by four beams. Okay, so there's a beam 1, 2, 2, 3, 3, 4, and 4. So four beams are there, and there's a gravity load, some dead load and live load, something kilonewton per meter square loads are there on top of the slab. And you want to find out how much load comes, how much kilonewton per meter comes to this beam, how much kilonewton per meter comes to this, similarly how much to this, similar, and how much to this. And if you want to calculate that, this tells you how to do it. So basically, you just you take the short side, draw a triangle with 45-degree angles. Okay, draw an isosceles triangle like this, 45, 45, and do the same thing on the opposite end. So how much load is covered within this area that comes to this beam? How much load is covered in this area that comes to this beam, and the remaining trapezoidal area, comes to this beam, and that goes to this beam. So, for example, if I have about total load on this slab is 10 kilonewton per meter square. Okay, then what you would particularly do is you would take the area of this particular triangle. Okay, multiply that by 10. Okay, and divide that by the length of the beam. That will give you how much kilonewton per meter comes onto this beam. And similarly, if I want how much load comes onto this beam, what I'll do is I multiply that 10 kilonewton per meter square with the area of this trapezium divided by the length of this particular beam. That will give me how much kilonewton per meter comes to this beam. So this is just something that you should know when you do a design problem, how to find the load which comes. So the 45 degree shown is general. It's for it is accurate, not accurate. It is much more appropriate when you have simple supports on all the four edges. If the support is not simply supported, if there are some supports which are fixed or something else, then the amount of load will have some variation. It will not be very accurate based on a 45 degree distribution. But still, this is what in general is used when you have this kind of four sides supported beam. So one thing that you will know is the extent of the loads transferred to the short edge depends on the aspect ratio and also on the support type at each edge. Okay, meaning that if it's all simply supported, then this works. If two sides are if two sides are fixed and the other two sides are something else, then it's different. Okay, slightly different maybe. So these are some things which you may want to do. So another thing to note is this is as far as calculating what the load on the beams are. Okay. So because when you do a design, you have a slab, you have to design the slab for the bending of that particular slab. Below the slab, you may have your beams, and you would also actually have to design the beams. Okay, depending on how much load is there on the slab. So it is for that purpose you have this representation. Okay. So you see that the extent of the loads transferred to the short edge depends on the aspect ratio. Okay. So what I can ask you, like, for example, so this is a rectangle. Okay, say that the length by breadth ratio is 2. Okay, and you have a certain load coming on this beam. Let me say that instead of a rectangle, I have a square. Okay. Then what do you think will happen? In which case does the short edge have more load? In the rectangle, in which case does it have a larger proportion of the load? In the rectangle or in the square? When is the proportion of load on the short edge more? For a square or for a rectangle of aspect ratio 2?
Square.
Square. Why?
So the area of triangle is more.
Area of the triangle is more, or no? All four will get equal amount of load. All four beams. So in this case, you see the trapezium is much bigger. So more proportion of the load goes to the long edge. So it depends on the aspect ratio. That is one thing. And similarly, just like the load, when you come to the moments as well, the distribution of bending moment along the shorter direction and along the longer direction, they will also change as your aspect ratio changes and as the type of the support changes. Okay. So if you take a small element over here, you may have some MY moment, some MX moment. And this is not that easy to find. Like for a one-way slab, it's very simple. You just take the shorter bending direction. You do WL square by 8 or whatever it may. You do WL square by 8, you get the bending moment. Okay, so that's pretty easy for you to do for a one-way slab. In this case, it's not one direction bending; it's two direction bending. So the bending in one direction will affect the bending in the other direction as well. So there's a kind of relation between that bending moment in both the directions. And this is not that easy to find. It requires a detailed analysis. So you will not be doing that level of detail in analysis. You have code book provided shortcuts to encounter such situations, which we will be using. Only thing that you should know is one thing is, if you look at this figure, this mx is the direction along the x direction. According to IS 456-2000, Ly represents longer direction always. Lx represents shorter direction. This is the nomenclature as per IS 456. X is short, y is long in general. Okay, so that's how it's shown over here. So when you look at this figure, you think, okay, Ly is larger, so therefore my bending moment along this y direction, you would think that should be more, because you know that bending moment means you take load. If the length is more, you get more bending moment. That's what you're used to, and therefore naturally you may think, okay, then my should be having greater bending moment, and mx should be smaller. But that's not the case. Actually, the opposite happens. So it's normal to think that my should be larger because Ly is longer, because bending moment is proportional to the length. However, that's not the case, because this edge is shorter. Okay, x is it's the shorter direction, so therefore it is easy for the load to transfer from a given particular point to the shorter edge. Okay, because this is closer. If I take a point over here, okay, if I take a point here, the load on this point or the load on this element, it's easier for the load over here to go to this end than to go to this end. Okay, so therefore in general more load transfers to the long edge, or transfers to the long edge in the sense it transfers along the short direction. So it goes along the short direction and goes to the long edge. Similarly, load transfers on this side as well. Okay, so therefore the section between the long edges, okay, in other words the short edge, it will get more bending moment, because this direction is shorter, more load gets transferred along this direction, and this direction is the shorter direction, so therefore the short edge gets more bending moment. And this is a key difference between beam action and what is known as plate action. Okay, the bending of the slab, which is a two-dimensional element, bending of a two-way slab rather, okay, it falls under something known as plate action. And this is a key difference, where your bending moments will be under a uniformly distributed load, and if all the supports are the same, you will have more bending moment along the shorter direction than along the longer direction. Okay, so this is a key difference. You have to remember that. Now, as I told you, it's very difficult to actually get what those bending moments are, because it requires what I can ask is probably your Euler-Bernoulli theorem for beams. You have a differential equation which gives you Euler-Bernoulli theorem. What is the order of that differential equation? Normal Euler-Bernoulli beam theorem.
Second order.
Second order. Okay. So you are able to actually, and it's only in terms of length, x direction. Okay. Y is a function of x, or a moment or shear force or whatever it is. It is a function of only x. In this case, you have a function of x and y. It's a two variable. You'll have a two variable differential equation, and not only that, the order of the differential equation will be fourth order. Okay, so if you want, if anybody is curious, they can Google Kirchhoff plate theory. Kirchhoff, the same Kirchhoff as you have seen in electrical circuits. Okay, the same spelling. Okay, you search Kirchhoff plate theory, you will see that there's a fourth order differential equation in x and y, a biharmonic equation. So solving that is not that easy, and unlike Euler-Bernoulli theorem, using that it's a headache for any general purpose. So therefore, nobody wants to do that. Nobody wants to solve such equations. So the code book gives us a shortcut known as, I'll show you these things soon. It gives you a shortcut in terms of moment coefficients, meaning that if you know the coefficient, you just multiply it with load and length square or whatever, and you'll get what the bending moment is in that particular direction. Okay, so it's based on a theory known as the Rankine-Grashof theory. So basically what it does is, if you have a slab like this, it takes a unit strip along x direction, a unit strip along the y direction. Okay, so you have two unit strips, 1 and 2, and they intersect at a particular region. What is said is, since you have an intersected region, within this intersected region, it's basically the same region. Okay, this intersected region is common to both 2 and 1. So therefore, if I take strip number 1, find out the displacement in this region, it should be the same displacement as taking strip 2 and finding the displacement in this particular region, because it is basically the same region. So using this particular aspect, that and at the displacement at this point, okay, if I take strip 1, should be equal to the displacement at the same point if I take strip 2 as well. And of course, D means like your EI, it's the flexural rigidity. D usually in plates you will use instead of EI, you'll use the letter D. Okay, the only difference is flexural rigidity, you have E into I. What is EI? What is E? What is I? For flexural rigidity and moment of second moment of area. Okay, so basically that is flexural rigidity. In plates you have something similar, except that not just E and I, you have also the term nu coming into the picture. Can you guess what nu is? Greek letter nu. E is Young's modulus. What would be nu?
Poisson ratio.
Poisson ratio, because it's x and y, so you have Poisson lateral effect also comes into the picture. So in terms of that, you have flexural rigidity along y, flexural rigidity along x. If it's a uniform thickness slab, dx will be equal to dy. So using these concepts, so you can just assume that this is simply supported and this is simply supported. 5 by 384 PL power 4 by. Instead of EI, I have written dx and dy. That's the only difference. And of course, the total load should be equal to the summation of loads coming from 1 and 2. Okay, so P not equals P1 and P2, and all the D's are equal. And relating all this, you can relate P1 and P2 in terms of the total load P0. And you see this factor in terms of Lx and Ly, they become some coefficients. And basically, this is the idea by which moment coefficients are derived. Okay, this is the basic idea. You will not be asked to derive it or do anything like that. But you should just know that there are different different terms will come. Okay, if this all are simply supported, you have just Ly per 4 by Lx per 4 plus Ly per 4, and similarly for P2 as well. If it's not simply supported, if we have random boundary conditions, the same thing, except instead of you'll have a coefficient along with it, Cy, Cx, etc. Otherwise, no real big difference. And based on this, you can just find out the bending moments, and you will write your bending moments as moment along x equals some coefficient times P0 times Lx square. My equals some other coefficient which is applicable to the y direction times the total load times Ly square. Okay, so it is basically this Rankine-Grashof theory which finds its place in IS 456 for designing or finding the moments in two-way slabs of different boundary conditions. Okay. Only thing you should remember over here is, unlike the original Rankine-Grashof theory, the coefficients which are derived over here are both derived with respect to Lx. Okay, so many people tend to make the mistake. They'll put mx is alpha x w Lx square, and my equals alpha y w Ly square. People tend to put by mistake. Okay, because it's natural to think that way, but that is wrong. Actually, both are Lx. Okay, all the moments are in terms of the short direction. Okay, so be aware of that. And these are the general cases which will also find place in your IS 456. Okay, interior panel. So there are basically 9 different. You can just read the terms. Interior panel: one short edge discontinuous, one long edge discontinuous, adjacent edges discontinuous, short edge is discontinuous, 2 long edges discontinuous, 3 edges discontinuous, 3 edges discontinuous with 1 short edge being just. So in this case, these 3 are discontinuous. This is continuous, the long edge. In this case, short edge is continuous. Or 4 edges discontinuous, meaning that like a simply supported slab. Okay, so this represents a discontinuous edge, this represents a continuous edge. Okay, so these are 3 different cases. Basically, what is the meaning of this continuous and discontinuous? Any idea? What is generally when you have a continuous beam? What actually does that word continuous support tell you? What is the meaning of a continuous support?
So there will be a bending moment at the.
So basically, there is a transfer of bending moment across the support. Okay, that is the meaning of a continuous support. It's the same thing with the continuous edge. Only this is a slab, so therefore you have an edge instead of an isolated support, instead of a point support rather. So that is the only difference. So if you have just look at this, so this is a floor system somewhere. Okay, so you have different slabs 1, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so so you people, I can just ask you some 3 different slabs and you can tell me what support condition it is with reference to the cases above. For example, if I take panel number 7, what case does this fall under? Panel number 7. Panel 7 falls under what case?
The 3 edges.
3 edges?
Discontinuous.
Discontinuous.
Discontinuous. Okay, so which edge is continuous, short or long?
It's a long.
Long edge, continuous. Okay, very good. So basically this, and similarly, if we come to maybe number 5, how about number 5? What case does this? By the way, these lines, these dotted lines, they are the intermediate beam supports. So yeah, 5. What case does it come under?
The 2 long edges continuous.
2 long edges continuous. Okay, or 2 short edges discontinuous. Okay, very good. So, and how about number 1?
It's the interior panel.
It's an interior panel. Okay, so when you're given a floor system, you should first be able to identify what type of panel it is. Okay, because when you look at the table in IS 456, it will list 9 different cases and the respective moment coefficients alpha x and alpha y for different values of Ly by Lx. I'll show the table fully. Okay, so all these are with as long as you have given provision to resist torsion at the corners. So this is also something that I had actually shown when drawing the detailing for one-way slab. In case you remember it, when I was drawing the one-way slab detailing, I told you at the corners you give a mesh of top and bottom reinforcement in 2 directions. Do you remember that drawing?
Yes, sir.
Yeah, so basically that is called as a provision for uplift or resisting torsion at the corner. So that's what you. So as long as you have that provision, you can use this table. If you do not have that provision, it's a very basic, simply supported slab. In which case you use table 27 instead of 26. All these tables will be shown to you, so don't worry too much. And so in this way, you can just calculate the moments and apply the reinforcements. So you basically divide your two-way slab into strips like this. Okay, so basically you have edge or column strip. It's called by both the names, either edge strip or column strip. Then you have something known as a middle strip. Okay. So when you look at, so this is defined for both the directions separately. It's defined separately for Ly. It's defined separately for Lx. So basically, what a edge strip means is the span by what do you say? The span by 4. Okay, no, the span by 8. Okay, 1/8 of the span from the edge. That is known as edge strip. It's present for this edge 1/8, this edge 1/8. So adding both sides together, you have 1/4 of the span is already gone to the edge strip, and the remaining 3/4 it's known as a middle strip. Okay. So likewise, you can also do it along the Lx direction. So you have Lx by 8, Lx by 8, and the middle 3/4 of Lx is middle strip. Okay. So all the reinforcements that you calculate, okay, so all those reinforcements you calculate out of this particular thing which you calculate, no, they are all applicable to the middle strip usually. Okay, they are all applicable to the middle strip whatever you calculate. So whatever you have calculated, both the negative and positive reinforcements that you calculate based on these bending moments. Okay, these are not bending moments, these are coefficients. Based on these coefficients you will find bending moments. Based on the bending moments you will find some reinforcements for positive and negative, and whatever you find in that way, they are applicable to middle strip. They are all applicable within this region. Okay, and you should actually so that's what it says over here, and the reinforcement should extend to within 0.25 L of a continuous edge or 0.15 L of a discontinuous edge, and in the middle strip continue at least 50% of the reinforcements to within 0.15 L. These things and all you will know only when we come to actually doing the problem and getting a drawing. Okay, doing the detailing, only then you will come to know this. So anyway, but anyway, it's I just want to put this into your mind right now itself, so that when we do the drawing you will not find it very new. And of course within this region you will give your I mean not in this region, at for a distance of L by 5 not L by 8, you will be giving the same 75% top and bottom mesh which I told you before. Okay, that thing will be given over here. Okay, so before I go to yield line theory, I'll just show you the appropriate things in IS 456. What page does this come? I'll go one by one. Scorbels, I go to page number 46. Okay. What is number 51? What page number is this? 38. Okay. Okay, so these things I think you'll know. So the Lbd ratios. So if you have a two-way slab, you can use these as the Lbd ratios, 35 and 40. Okay, so just read this for two-way slabs of shorter spans up to 3.5 meters, and if you have mild steel reinforcement Fe 250, then the L by capital D, not small d, L by capital D ratio may be adopted to this. Okay, as long as your loading is about within 3 kN per meter square. Okay, 35 or even more than that you can use, it's not wrong. And if you have Fe 415, Fe 500 bars, you just multiply these values by 0.8, and you can. So why do you need this? Just so that for a deflection check. So if you provide the thickness of the slab should be at least such that the Lbd ratio is lesser than this. Okay, so this is one thing, and then other things with respect to reinforcement. Yeah, this is one thing that you can see. A slab spanning in two directions at right angles. Okay, so this is what we are talking about, two-way slabs. So the slab spanning in two directions at right angles and carrying uniformly distributed loads may be designed by any acceptable theory. So the meaning of this any acceptable theory is, like what I showed you in the PPT, that Rankine-Gashov theory. So there are several theories which you can use. There is this Rankine-Gashov theory. There is yield line theory. Okay, which I will be coming to next. But using these theories are not the most straightforward method. It's not the easiest method to use. That's why you have this coefficients. So you can use those methods, or you can use the coefficients given in Annex D. That's what is mentioned over here. Somebody's not muted. Okay, muted. Okay. So some such methods which are used are Piguet's curves or Westergaard's theory. Okay. But the most common one is the most common theory is yield line theory. But even that we don't use too much. We use only the Annex D coefficients. All right, so then going down to reinforcements. Tension reinforcement negative. So these things and all you've already seen. I mean, shear reinforcement, columns, torsion reinforcement. So these are all for columns. Okay, I think this is about done. Okay, I'm disabling the mic for everyone today. Okay, because I'm not able to find out who that idiot is. Okay, this is flat slabs. This is flat slabs. Okay, so I think I can go to Annex D. Annex C. Annex D. So this is the one that you will use when you get a problem to design for two-way slabs. This is the formula to find your bending moment in any given direction. Okay, the same thing which I showed in the PPT. W is your load. Okay, dead load, all your gravity load, that is W. Lx is your short direction, Ly is in the longer direction. Alpha x and alpha v are the coefficients as given in the table, which is there in the next page. Okay, and this is what I told you with respect to middle and edge strips. Okay, and the middle strip is 3/4 of the width, and each edge strip, two edges are there, so each edge strip is 1/8 of the width. The maximum moments calculated in according to the coefficients which you have obtained. Okay, so according to the coefficients, whatever thing the moments that you have obtained, they are applicable only to the middle strips, and for the remaining part, which is the edge strips, you will have to actually make a continuation of the bars, okay, for a certain distance. Okay, as discussed below in this points D 1.4 and D 1.5. Okay, so if you have a continuous edge, then extend it to a distance of 0.15. If you have a discontinuous edge, extend it to a distance of sorry, if it's continuous, extend it to 0.25, and 1.15 if it is continuous. So even if you have a discontinuous edge, don't leave the top of the slab without any reinforcement. Give it a minimum reinforcement equal to 50% of the reinforcement in the midspan. Okay, because they say that whenever you have a slab, you need to connect it to the beam or to the wall on which it is supported, and because of that particular connection, you may have some moment coming on some negative moment coming on that particular slab. So in order to take care of that minimum negative moment, about 50% of the midspan reinforcement you will have to extend to take care of the negative moments. The torsion reinforcement I've already talked about. 1/5 of the short span direction, you give top and bottom layer of 3/4 of the area of positive moment reinforcement. Okay, so this is where I took that figure from. This is the main thing, the table which you're going to use. So you have here the type of panel and the moments considered, the short span moment coefficients alpha x, and the long span moment coefficients alpha y. Okay, so one thing you'll notice, this alpha x depends on what is the aspect ratio. I have moments, I have coefficients right from 1 to 2. Why is the range only from 1 to 2? So anyway, I cannot. I hope you know the answer. It is because your Ly by Lx is 2, and because of that particular reason, our Ly by Lx limitations are given between 1, because when it crosses 2, it becomes a one-way slab, and then none of these are applicable. And for each of this, you have two cases of moments: negative moment at the continuous edge, positive moment at the image span. So on every out of 9 different cases, for 8 cases you will have both negative and positive moments. Okay, if you look at all of this, negative moment, positive moment, negative moment, positive moment. So like that, it is there for all the 8 cases where you have at least one continuous edge. If you have at least one continuous edge, you will have both negative and positive moment coefficients. If you have for the only case where all the 4 edges are discontinuous, you do not have any negative moments, you have only positive moments. Okay. And there used to be one mistake in this table. Let me see if I remember it. One short edge discontinuous. Yeah, 2 and 3. So this is actually one short edge continuous. This is actually one short edge discontinuous. It's a mistake. Okay. This is one short edge discontinuous, one long edge discontinuous. Okay. One short edge continuous is present over here, number 8. Okay. So this is a mistake. This is one short edge discontinuous. So anyway, so what you'll do is when you will first job is to identify what panel it is. Once you identify the panel, calculate its aspect ratio. For example, if the aspect ratio is say 1.4, and you have a slab which is adjacent edges are discontinuous, for example, then you'll come to this number 4, and you just go and pick out the value of the particular moment coefficient for negative moment and particular coefficient for the positive moment for x direction. And then you will do this, but so for getting the positive moment along the x direction, you will do this 0.071 into the W, whatever load you have, into whatever is the length of the short span, Lx, that squared. So that will give you along the x direction what is the moment kilonewton per meter. Okay, so you will get that first, and then you will also get if you do 0.053 into the same load into the same Lx square, you'll get some moment which is the positive moment. So this is negative and this is positive moment along the same direction x. And unlike the x coefficients, the y coefficients are all one single value for every case. Okay, it does not depend on the aspect ratio Ly by Lx. The reason is, since the answer is over here, if you look at this particular case, okay, both are Lx square. For mx also it's Lx square, my also it's Lx square. If it had been my equals alpha by W Ly squared, then for long span coefficients also your alpha y will depend on on the Ly by Lx will have 1, 1.2, 1.3, 1.4, etc. And because it is also being related to Lx, you have just one single value over here. Okay, so this is something that is unique about this particular table. Okay, and if you have so this is as long as you have this thing, 4 sides with provision for torsion at the corners. So this table is applicable as long as this is there. If there is no provision for torsion at the corners, then it's a very normal simply supported slab, and you can take these coefficients for the positive moment. It's simply supported, so therefore there will be no negative moment. Okay, so these are the coefficients that you have, and you can also perhaps have a look at the drawings or the how to do the detailing. Hmm. 119. Okay, so this is, I think I showed this before. When I was teaching for one-way slab, I also told you what difference comes if you have a two-way slab. So basically the same thing, except that you have your two directions. You have both um, bent bars and straight bars. Okay, and this bending distance is 0.1 Ly or Lx, depending on which direction you're doing. Same thing you can show in the plan or the sectional elevation. So this is general arrangement. Very similar drawing that you had to your one-way slab, except that instead of giving your reinforcement along one direction, you will give it along two directions. The only difference. Okay, and so this is just a representation of edge strip and middle strip. Not much important. I mean, nothing very new is depicted over here. Torsion reinforcement you have seen. Okay, this you did when you are doing a one-way slab as well. How to give the bent up, and this is also, I think it's been covered. So basically, this is how you actually. It's just basically the reinforcement detailing is just a reproduction of one-way slab reinforcement detailing, except that you'll give it along two directions instead of giving it along only one direction. Okay, so this is what is. There's a few things that I wanted to show you on this. Now we'll move back to the PPT. And since I'm moving back to the PPT, I will once again enable you. Okay. So, so what I have covered till now is two-way slab. What is the principles? What is what the differences are? How to use? What these moment coefficients mean? What are the different boundary conditions? 9 different boundary conditions which can be present for a two-way slab, and how to take the moment coefficients? How to find the moment? After finding the moment, there's nothing else to teach, because checking the thickness of the slab, finding the reinforcement percentage, and all those things, it is the same as doing for a beam. Okay, for example, if we find mx is say 30 kilonewton meter per meter. Okay, say something like that. Okay, so what you'll do is you'll check the same thing. You'll put that mu limit equals to 0.133 FCKBD square. Find out d. Same thing you'll do with the my moment, positive and negative. And out of all these cases, you'll pick out for which case is the maximum depth or thickness required. And you will increase that, and you'll give some thickness for the slab. And based on that, again, you'll use the same, based on the same moments, you will find out what is the percentage of reinforcement along the x direction for positive and negative moments. Based on the formula, 50, what's the 50 FCK by F by 1 minus root of 4.59. The formulas there, no? So you'll use the same thing to find out the reinforcement for all the moments. Positive moment x and y direction, negative moment x and y direction. Okay, so these are all things which you once you know, these are all straightforward procedures. Tomorrow when we do a problem, we can find we'll know how to do it. Now, one final thing that I want to cover, I'll probably give you, the time is 4. I'll probably give you about 5-10 minutes to I'll give not 10 minutes, maybe 5 minutes. I'll give you, just take a break. Okay, and after that, I think only Actually, it's up to you. Do you want to break for 5-10 minutes, or do you want me to continue it and finish it? Your mic is enabled now. Mic is enabled now. Your mic is enabled. Do you want me to continue, or do you want me to give a break?
Break would be fine. 5
Break.
minutes break.
Break. Okay, fine. Take 10 minutes then. It's 4. Around 4:10 we'll continue.
Thank you, sir.
Yeah.